Welcome to week 5 of today's maths class, and today we are going to be looking at functions, mappings, and matrices. Hopefully you've been following quite along from the beginning of week 1 up until this time, and most of the topics that we've covered have been explained in detailed form and to your understanding, I hope. So a lot of what we do in the subsequent classes build on what have been done in previous classes. So which is why I'm emphasizing on the fact that you have to have been following up from the beginning. So it's important, especially for those that are coming in, so this is your first class, to go back and watch the recordings. I think they are available, so you get an idea of the concept that we've already discussed, and then you can now be able to build on them to understand what we talk subsequently. Because like I say, everything that goes on is building on what has been taught before. So for today's topic, we're looking at functions, matrices, mappings, and matrices. So we asked the question, what are we supposed to have learned after the end of this class? So we're supposed to understand what functions are, understand how to map those functions, and then go into matrices, understand the concept of matrices, how to operate with them, and then know how to do basic arithmetic with matrices. So functions. So what's the function? A function pairs each domain element with exactly one codomain element. And that's a lot of grammar. In layman terms, what do we mean when we say function? The function, as we represent in most of our discussion going forward, is represented by f of x. Now, what does that mean? It means that in our function or in our equation, this x that is in bracket now is the variable, is the unknown of our function. So, for example, this one that has f of x now is equal to x equal to 2. You see that the variable in our equation is x because the function is a function of x. So when I say f of x, I'm saying a function of x. And because this is a function of x, every variable will have x in it. Now, if this was f of y, then it would simply mean that I would have to have y variables here, right, in my equation. Also, if this was f of z, it means that variables I would have would be only z variables, right? Now, I could also have something like f of x, y. Now, what would that mean? It would mean that in this equation or in this function, I could have a combination of x and y variables. So maybe I could have something like x, y plus 2x plus 2. So now you can see that I have the x variable and the y variable. So basically, I was defining what I mean when I talk about functions. So when you see this illustration here, in this example, f of x, it means function of x. It's written f, is read f of x, but it means a function that has x as its variables. So in this instance, we are saying that in the equation or the function of x, the variables we are going to have will be only x variables, right? And to make that clearer, I made another example that if this was y here, so it means function of y. It means that in the function itself, the only variables you have the y variables. So you would have y plus 2 instead of x plus 2 because now you're working with the y function. If you had f of z, your variables will now have to be z variables alone because the function is only that of z. Now, you could also have a combination of variables, right? So you could have something like f of x and y together. And then it means that in your function, you can combine both the x variable and you can add the y variable as well in whatever combination you want. But the point is that both the x and the y variables are involved. Now, this is the basic definition, basic representation of a function, right? Now, the definition here says it pairs each domain element with exactly one codomain element. Now, what does that mean? So we would have to define what the terms domain and codomain actually mean. Now, when we are talking about functions, right? If I were to give you this equation and tell you, okay, so let's go back to our original equation. Here we have f of x, right? Now, if I were to give you this equation and tell you that f of x is equal to 2, and I now tell you to find or to calculate for me f of 1. Who can tell me what you will do to find f of 1? Just unmute your mic and tell me.
2 minus 1.
Why do you say 2 minus 1?
Because I'm guessing x is 2, so 2 minus 1.
So where does the minus come from?
I thought it's 1 divided by 2.
1 divided by 2. Let me re-ask the question. So I said you are giving an example, right? That f of x is x plus 2. I hope you can all see my screen. Right? F of x is x plus 2. And now you are asked to find f of 1, right? What would you do? What would this f of 1 now result to? You've been given that f of x, x plus 2. Now you're asked to find f of 1. What would you do and what will your answer be?
1 plus 2.
1 plus 2. HBK, is that your answer or do you have something else?
Yes, sir. Yes, sir. 1 plus 2.
Why would you do 1 plus 2? Explain to me why would you do 1 plus 2? Since both of you have
Okay.
said that is the answer.
Okay. Since f of s is equals to s plus 2.
Okay.
I hope you understand me. So f of 1 will be 1 plus 2 now. Will be equals to 1
Right.
plus 2.
Okay. So fantastic. So you understand that if by telling you f of 1, if they are telling you that anywhere you see x, you should replace it with what? 1. And so f of 1 will be 1 plus 2, and the answer to f of 1 will be 3. Right? And that applies for any other example of a function that you might be given. So if you give you f of any variable, in this case of x, and now you're giving you f of a constant term, you simply replace that variable with the constant term, and then you're able to find your answer. Now, this brings us to the concept of domain and codomain, right? Now, when you are talking about functions, we have two concepts. We have the codomain and we have the domain, right? Now, the domain is the input, while the codomain is the output. Now, in this question, f of 1 is going to give us 3, right? Because 1 plus 2 is 3. And that's pretty obvious. Now, what we have here is that for this function f of x, f of x is equal to x plus 2. If you impute 1 into this function, your output is 3. Likewise, if you input 2 into this function, your output is what? 4, because 2 plus 2 is 4. If you impute 10 into this function, your output is what? 12. Now, you are seeing that for every single input you put into this function, you get a corresponding output. Now, the input is your domain, and the output is your codomain element. So here we understand what and see how this definition of a function comes about. That a function pairs each domain element with exactly one codomain element, such that if you have a function and then you have an input element, you get a corresponding output element, right? And that's where the relationship from functions and mappings now come to. Because if for a function, you have to put in something and you get out something. It's like what can I use as an analogy now? So like when we talk about computers, right? Input devices and output devices. You put in data and the computer gives you what? Information. So it's kind of similar, right? You put in a number into this function, right? The function now, based on whatever the function is, it processes it and then gives you an output. And so in a sense, you can say that this input is the corresponding output of the input for this particular function.
Yes, is this function of a thing, is it the same stuff that's in Microsoft Excel when you're trying to input values? Where they have
No, so not
fx stuff.
no, not necessarily. So here we're dealing with algebra. So I don't exactly know what you're talking about in Excel, but I don't think that's the same concept. So but then as you go ahead, Sha, it will become clearer with more examples. But so for now, let's just continue. So we have types of functions, right? So we have one-to-one function, onto function, and bijective functions. There are other names for these ones, which are named here in brackets. Now, for a one-to-one function, no two inputs share the same output, right? So it means that, so for like this example now, I can say that this is an example of a one-to-one function because Well, it might be, because now if I put in 0 here, f of 0, my output is 2. If I put in f of 1, my output is 3. If I put in f of 2, my output is 4. So for every single number I put in, I get an output that is different from any other output I can possibly get. So my output never repeats itself. And so it is a one-to-one function. It means that every input I put in has a unique output. The output is always different from whatever output I can get from another input. So every input goes to one output. Every input goes to one output. Every input goes to one output. So kind of one-to-one, one-to-one, one-to-one. So that's where the name actually comes from. One-to-one input. One-to-one function or injective function. So no two inputs share the same output. Everyone is on its own, unique. That's one type of function. Now the next one is the surjective function or onto function. Now this one is not necessarily a unique function. So some inputs can have an output that another input will have. Now a practical example is the function f of x is equal to x squared, right? So let's use y so that it's different. F of y is equal to y. How do I represent that? Y squared. Okay, fantastic. Now, if I were to put f of 2 here, my output would be what? 2 squared is 4. If I were to put f of minus 2, my output would be minus 2 squared, which is also what? 4. So here we can see that 2 as an input in this function, f of y, gives me 4. And minus 2 as an input in this y also gives me 4. So I'm seeing two inputs that are giving me the same output for this f of y function. So you can see that it's not unique, right? Two different inputs can point to one same output. And so this one is an example of an onto function. So every codomain element is an image of some domain element. When they say image, it means that you can find a corresponding input for it, but then they are not always unique, right? And then the bijective function is a combination of this and this. So these are the type of functions that exist. Now, to now define the terms domain, codomain, and range, so that we can actually understand what they mean. So the domain of a function is a set of all possible inputs for that function, right? So if you go and take our first example, f of x, it is equal to x plus 2. What is the set of all possible inputs for the function? That is the domain of this function. It means all the possible numbers that can serve as input for this function. Now, if you think about it, is there any number that you put into this function that will not make the function to work? And I don't think that exists, right? So you can put any number from minus infinity up until infinity. Any number you put in this function will work. Any number you put in this function will work. So in that sense, the domain of this function is all the real numbers from minus infinity to infinity. Now there might be a case where the domain of a function will be limited, and an example is where you have functions that are fractions. So for example, let's use f of z now. We have that f of z is equal to what can I use as an example? Okay, square root of find my square root symbol. I don't think this keyboard has a square root symbol. Well, I wish I could just draw this on the screen, but let me use this to represent square root. So square root of z, right? Now, so imagine this is a square root symbol. Unfortunately, I do not have that on my keyboard at the moment. Now, we both know that we cannot do square root of negative numbers, right? So we know we can say that you cannot put negative numbers into this function because the function would simply not work. And so you are now limited to the kind of numbers you can put into this function, and you are limited to only what? Positive numbers. And so if you are now asked to define the domain of this function, which is the set of all possible inputs for the function, it means that your domain is only from 0 to infinity, to positive infinity, which are only positive numbers. Okay, we see a case where the domain of a function is limited. Now, likewise, the codomain is the set containing all the potential outputs, right? So all the possible numbers you can get from your answer is the codomain. Now, for this first example, we see that our domain is what? It can be anywhere. It can be all possible numbers we can get, because our input is also all possible numbers. And so you can get any kind of number from your domain. Now, for your codomain, you can also be, the answer can also be all possible numbers. Now, why is that the case? Because square roots can either be this, your answer of the square root can either be the negative answer or the positive answer. So, but then we know that our domain is only positive numbers, because you cannot do square root of a negative number, but you can get a negative number as a square root answer, right? So your codomain is all the possible numbers from minus infinity to infinity. And then your range is the actual set of outputs produced by the function. So you now set a range and say the answers I get range from this point to this point for my function. So these are the definitions of terms that you use when you come across functions and mappings and how they are applied. So the next thing you need to look at now is composite functions. Now, composite function means we are combining two functions together. So in this example, we are combining f of x and g of x. Now, the representation for composite functions can vary. So there are two different ways of representing composite functions. So I'll use this example to illustrate. So here they give us g of x as x plus 2, and they give us f of x as 2x. Now, this is now a composite function. So they are telling us to find f of g of x. I hope you are following. So this is where I'm looking at. They're telling us to find f of g of x. Now that's the composite function. Another way this thing can be written now is by this, by f o, so like a small o in between f and g. So it's the same representation of this f of g x. Now, what does this mean? Now, this is a composite function because why? We are combining two different functions into one. Now, how does that work? So, first of all, the inner function is going to be of your base function, right? So, the inner one in this case now is g of x, or if you are using this representation, the first one. So, or the second one on the right. Now, the composite function is f of g of x. Now, what does that mean? It means that f is the outside one. So we do the inside one first and then do the outside one. Now, g of x is what? From our function. We are told that g of x is what? X plus 2. So what we do now is replace g of x with what? X plus 2. So now we have f of x plus 2, right? So now how do we simplify this? Now we know that when we are given a function and we are given an input for that function, what we do is to replace that input wherever we see the variable. So for example, if we are given f of 1, what we'll come and do is to replace 1 with wherever x, where we see x, we replace it to 1. But now we are given f of x plus 2. So what are we going to do? We are simply going to come and replace x wherever we see it was x plus 2. That's it, how it works. So now what we are going to have is going to be equal to 2. And then now we have what? X. So what we are supposed to do is x plus 2. So now we replace x with what? X plus 2. And that will give us 2 into x plus 2. And then you in the bracket, that gives you x plus 4. So this is how we simplify composite functions. Now, also note that g of f of x is not the same thing as f of g of x. Now, an illustration. So if this question was turned the other way around and you were given g of f of x, right, it will be different because now the order is different. It's not rearranged. So what is inside was f of x. So you start with that one and then go outside. So you were to solve this one now. we'll start with what's inside. What's the fx? Fx is 2x, right? So what we'll do now is to replace fx 2x. So we'll have g of 2x. Fantastic. Now, what will be the next thing we'll do? We know that we have g of x as x plus 2. Now we are told to find g of 2x. So it means that wherever we see x, we replace it with what? 2x. So our g of 2x will now be 2x plus 2. So you see that the answer for f of g of x is not the same with the answer for f for g of x, because multiplied functions are dependent on the order in which they are arranged. They are not interchangeable like that. And so you have to know when.
Yes, sir.
Okay, yeah, go on.
From the example, it says, from the first example,
Yeah.
if, like my question is, if f of x, if g of x is x plus 2, which is stated in the bracket there, why
Yeah.
is f of x not 2x? Why is it just 2?
F of x is 2. No, so this is the question you are given, right? This g of x and f of x are given to you already. So I don't know, what is your question exactly? Whitney, could you repeat
G
your
of
question so
x,
I
when
understand?
solving, g of
Yes.
x is x plus 2, which is indicated in the
Yes.
brackets, right?
Yes. Are you talking about this one?
G of x is x
Yes,
plus
g of
2, which
x is
is
x plus
indicated in
2.
the brackets.
Yes. I'm
And then
listening.
f
Go
of
ahead.
x is supposed to be 2x. Why do we have 2 outside the bracket, not 2x?
Oh, so
Why
yes,
do
that
we
was what
have
I explained.
2
That
outside
was
the
what I
bracket
explained.
instead of 2x? Because f of x is 2x.
So that was what I explained. So the order matters, right? Now, the composite function they give you is f of g of x, right? So like I said, you start with the one that is inside, then you now do the one that is outside. So the question gives f of g of x. So the inside one is what? G of x, right? And from what you were given, we are told that g of x is x plus 2. So you replace this g of x with what? The equivalent, which is x plus 2, right? So f of g of x will now be what? F of what is g of x? G of x is simply x plus 2. So you just replace it, right? And that is x plus 2. So what I'm saying is, when you are given a composite function, you start from the inside one, right? So g of x is given to us as x plus 2. And we are asked to find f of g of x. Now, starting from the inside one means resolving g of x first. We are given g of x as x plus 2. So we can simply rewrite this thing that's here as f of x plus 2, because we know already from the question that g of x is x plus 2, which is why I rewrote this as f of x plus 2. Now, how do you now resolve f of x plus 2? Because in the question, you're already told that f of x is 2x, right? So now what is f of x plus 2? It simply means that anywhere you see x in the question, you replace it with this new input. So x plus 2 now is your new input. So instead of having 2x, we're now going to have that f of x plus 2 is going to be equal to 2 into what? Anywhere we see x, we replace it with what? X plus 2. So instead of having x here, we now have x plus 2. And that's how we arrived at what we have here, 2 into x plus 2, which opens up into 2 into x plus 4. I don't know if that's clear enough. And so let me write an entirely new set of functions. So let me say f of z is 3z is 3z minus 1, right? And I'm giving g of z as 5z. G of z, what are we giving as g of z in this question? G of z is what? 5z, right? Right? 5z. So instead of having g of z, I now replace it with what? With 5z, because that's what g of z is. So this is now going to be f of what? 5z. Fantastic. Now I know that f of z is what? 3z minus 1. But now I'm asked to find f of 5z. So what does that mean? It means that anywhere I see z in this equation, in this function, I replace it with 5z. Simple. So instead of having 3z minus 1, I write the 3. So I rewrite everything, but then anywhere I see z, I replace it with 5z. Now I write 3, and now I've come across a z. So what do? F of 5z, I replace that z with 5z. So this is now going to be what? 5z and then minus 1. Right? And if I simplify this, that simplifies out into 15z minus 1. So that's how it works. Now, if I were to do g, so now what we have here is f of g of z. So like I told you, if you reverse it, it's not going to be the same thing. You now have to solve it again, starting with the inside one. And if I was given f of g of f of z, what would I do? I will start from the inside again. So I will replace f of z with what f of z stands for. And f of z, as you can see, is 3z minus 1. So I'm going to replace that f of z now with what? G into 3z minus 1, right? And now I'm going to now do g of this, which means anywhere I see z, I replace it with what? 3z minus 1. So g of z is what? 5. Then I replace z now here with 3z minus 1. And I open the bracket, right, and I write 3z minus 1. And that will now simplify into 15z minus 5. So this is how composite functions work. I don't know if it's clear now. This is how you resolve them. So you start from the inside function and then you work your way out, and then so you can have as many composite functions as possible. You can combine 3 or 4 or 5 functions for you and tell you to calculate the composite function. But you follow the same process. So you start from the inside and work your way out. You are able to get to the end of it. And that's how you resolve it. I don't know if this explanation is clear now to everyone. How did I get?
Minus 5.
There's not mine. Okay, I mean, if you open this bracket now, so 5 times 3z is 15z. 5 times minus 1 is minus 5. I simply open the bracket.
Okay, sir.
We have example of.
Okay.
Can we have an example of like 4 composite functions or 3 composite functions?
Something like that. So it will pretty much work on the same concept. It's just that you start inside and then you go out and you go out. So I'll just do one so that I illustrate what it looks like. So let me clear all of this. Oh, no, not all of that. All of this. Why is everything clear? So let's use the same example now, but let's add another one. So let's say I was given, so I have f of z, I have g of z. So let's say I was given h of z as z squared. Right? And then I give you f of g of h. Right? And this is the composite function. And I tell you to calculate this. So, like I said, you simply repeat the same thing. You start from the inside out. Now, what's the innermost one? Is h, right? So, what do? You rewrite it and then you start from the inside one. So, this is f of g of. So, what is h of z? H of z is what? Z squared. So, z squared, right? So, you place that and you close the brackets, right? Now, You resolve h of z. What do you do now? You do the next inside one, which is g of z squared. Now, what does that mean? It means that you resolve g of z squared. Now, we already know that g of z is 5, right? So doing g of z squared would be to replace anywhere you see z with z squared, and that would be 4. So instead of having 5z, right? And now that's f g of c squared. Now the last thing to do is now to do f of 5c squared, which simply means that anywhere you see c, you replace it with 5c squared. And now that will be 3 into 5c squared, and then minus 1. And if you open that bracket, I'll give you 15 squared minus 3. So simply following it from the inside out gives you your final answer. So it's as simple as that. So it works on the same concept. Even if you had up to 5 or 6, you simply just continue to it. So you start from the innermost one and then you work your way outwards. So I think that's clear. If there are any more questions, just hold them. At the end of the class, you can ask them as well, so that we proceed with what we have left. So the next thing we're going to be looking at now is inverse functions, right? You can be given a function and you'll be asked to find the inverse of that function, right? So basically the inverse, so if you have a function, like we explained before, you have a function, you have the input, and you have the output, right? Now, the inverse of that function is the function where you put in that output and to give you back the original input, right? So it's like a reverse of the original function we have. Now, an easy way to find the inverse of a function, an inverse of a function is represented by f to the power minus 1, f inverse. It's called f inverse for short, but the representation is f to the power minus 1x. Now, if you are given a function and asked to find the inverse, so here we are given that f of x is 3x minus 5, right? And we are asked to find the inverse. Now, how you simply do this is by solving it like a normal equation. So this f of x, now you replace it with something else just to aid you to solve it, right? So let's call another variable. Let's say y. So y is equal to 3x minus 5. Now, what do you do from here? You now try to make x to be the solution of the formula so that x stands alone. So doing that, we'll simply have y plus 5 is equal to 3x, and then making x with the formula will mean that x is equal to y plus 5 over 3. Now, having made x with the formula, you now reverse what you did initially. So now you replace that x with f inverse of x, and then you replace the y with x. So f inverse of x plus 5 over 3. So now this is the inverse function of f of x is 3x minus 5, f inverse of x plus 5 over 3. So that is, of course, corresponds to the answer we have. Now, if you were to put in, so like, for example, you put in 1 as in f of x, let's say you're asked for f of 1. If you put in 1 here, the answer you get to be what? 3 times 1, 3 minus 5 minus 2. Now, to confirm that your inverse function is correct, since inputting 1 here gives you minus 2 as an output, for the inverse function, inputting minus 2, which was your output here, should now give you 1. And if you check that, it's going to be correct, because minus 2 plus 5 is 3, 3 over 3 is 1. So that's how the inverse function works, where you have to find the inverse of the original function. And so what we do is simply just to make that x solid formula, and then whatever you get, replacing it now with f inverse of x is the inverse function. So that's how this works. I hope that's clear. If there are any questions, like I said, just hold on to the end of the class and we'll take everything at once. So we've already gone through the injective, surjective, and bijective functions. We talked about types of functions earlier. So those are the basic concepts in understanding what functions are and how to um, apply them and solve basic arithmetic and algebra that arrives from function calculations. So now we're going to move into matrices. We're going to move into matrices. So what's a matrix? Matrix is a rectangular array of numbers arranged in rows and columns. A rectangular array of numbers arranged in rows and columns. So a matrix is like a representation of elements of this. So remember when we did sets, right? So what we have set A has two number of elements, and you remember those elements are all written in a straight line. So that was actually a type of matrix in the sense, but you know, it's limited if I was to use that word. So now matrices we have arranged in rows, so something like what you have in this picture. So the horizontal direction represents the rows, and then the vertical direction represents the columns. So it's important to be able to identify that. I can remember the first time when I was in rows and columns, I always found it hard to identify whether the row was vertical or the horizontal. But it's something that you should be able to master. Obviously, to take a while. But yes, I mean, you should know that the row is horizontal from now and the column is vertical from now, so that it helps you when you are going to solve the matrices. So these matrices have dimensions. So unfortunately, I am not able to represent these matrices properly or text PowerPoint on the same slides. But however, the way they should be written in rows and columns. So just something like what you have in this picture here. So this way, rows and columns. So if you have to have a matrices have dimensions, right? So if you have to represent this in rows and columns, the row is normally not written first in dimension, column follows. So when here they talk about a 2 by 2 matrix, what do they mean? It means that a 2 by 2 matrix is one that has 2 rows and 2 columns. Or say a 1 by 3 matrix, it means that that matrix has what? 1 row and 3 columns. If I were to say a 5 by 6 matrix, it means that that matrix has 5 rows and 6 columns. So just for example, it would mean that this matrix here has what? So you count the rows first, 1, 2, 3, 4, 5, 6. And then you count the columns 1, 2, 3, 4, 5, 6. It means that this is a 6 by 6 matrix. So like I said before, the representation here is not really ideal because it makes it look like everything is a straight line. However, these 3 and 4 now should be somewhere. Let me see if I can even get that to work. Should be under this one and so something like this. That's perfect. So where you have row and column. So this is row 1 and row 2, column 1 and column 2. So this is what a matrix should look like. Ideally, here you have the rows and columns. So this is a 2 by 2 matrix because we have what? 2 rows, 2 columns. Fantastic. So we move on to the types of matrices. So we have the row matrix, the column matrix, the square matrix, zero matrix. Of course, there are numerous more examples, but these are the basics that you need to know. So what's a row matrix? A row matrix is a matrix that is only consisting of one row. So just one straight line matrix. So now the columns can be as large as possible, but then what makes a row matrix is that there's only one row of numbers. So kind of like what you have in the sets, right? The set has only one row of numbers. Sets are row matrices. Now, the column matrix is simply one that has only what? One column. And then it's just a straight line. Something like just one column downwards. And then you can have as many rows as possible, right? But then what makes a column matrix? It has only one column. And that means look at the square matrix. So what's the square matrix? And square matrix is of significant importance solving math. because more often than not, you come across K, you should come across K with square matrices, right? So square matrices are basically one where the row and the column has the same dimension. So this is our first example here is a square matrix. Even this one here in this picture here is a square matrix because the row and the column have exactly the same dimension. So this is 2 by 2. So this is square matrix. So basically, from the name square, you should know, right? The length and the breadth are equal in the square. So if the dimensions are not the same, then it's mean by the square matrix. Right? So 2 by 2, 4 by 4, 5 by 5, 6 by 6, all of the square matrices. Now, the zero matrix, which is the last one we have here, is basically a type of matrix in which every single member or element of that matrix is zero, no matter what it is. Every single element is zero. So that's what it means to have a zero matrix. So now I can see this 2 by 2 matrix here that I have elements in it, right? I have 1, I have 2, I have 3, I have 4. But imagine if all of these things were zeros. And that's what it means to have a zero matrix. So there are further explanations given here. Row matrix, which is a single row, column matrix is a single column, and square matrix is the number of rows equal to the number of columns. We already explained that. And zero matrix is all operations are all elements are zero matrix. Yeah. So with that explanation, move on to the matrix operations. Now, for addition and subtraction in matrices, any matrices of the same dimension can be added or subtracted, right? So we have an example here. Now, one of the first condition you have to note where it is stated here is that only matrices of the same dimension can be added or subtracted. So before you even say that you want to add two matrices, you first should check their dimension. Are dimensions of this matrix equal? If they are not equal, then you cannot perform addition, because each element in the first matrix has to match the corresponding element in the second matrix, so that they are able to keep, maintain the same dimension. The output, the result will maintain the same dimension. So in this case, this is possible because this is a 2 by 3 matrix. Now, why is it 2 by 3? Because it has 2 rows and it has 3 matrices. All right, so this is a 2 by 3. Now, the second matrix is also a 2 by 3. So once you conclude that, once you can see that the dimensions of this are not exactly same, you cannot add them. But if you see that dimensions are the same, then you can go ahead. So in this example, dimensions are exactly the same, and then you proceed to adding both of them. So you just add like normal addition and subtraction. So, but then the element in row 1, column 1 matches to the element in row 2, column 2, and like that. So 3 plus 2 here, 5 on this corner, minus 4 plus 6 here, 2 on this corner, 2 minus 1, 2 minus 1. So we see that in the output of an addition and subtraction matrices, the order of your answer is going to be exactly the same as the order of your inputs, because the answer here is also what? A 2 by 3 matrix. So that's how you know that what you've done is correct, irrespective of whatever. So the answer is always a 2 by 3 matrix. Now the same thing applies for subtraction, right? The only difference is that the sign now changes, but the other conditions I've listed must remain the same. You must be able to be and which is the same dimension before you can carry out addition or subtraction. Now the next thing we're going to be looking at is scalar multiplication, right? So if you have two matrices, one matrix actually, so a matrix A, you can multiply that matrix with a scalar number. So what is a scalar? Scalar is just a random number, a constant, 1, 2, 3, or any number can multiply that matrix. So for example, this 2 by 2 matrix A, if I were to say I want to now write 2A, which means I want to multiply A by 2. And so what does that mean? It means that 2 will multiply every single element in the square matrix. So now my A will now be 2, 4, and then 6, 8. So scalar multiplication is just like opening a bracket, right? Every single thing in that bracket is going to be. And so in matrix, it's no different when you multiply by scalar. So the scalar multiplies every single thing, right? And now the third one is matrix multiplication, right? So we have A times B resulting in C in matrix multiplication. Now, in matrix multiplication, we have some rules that you have to follow, right? Because multiplication in matrices is not exactly as straightforward. So when I say multiplication matrix, I mean now multiplying two matrices, not scalar multiplication like we talked about over here. That's very easy and straightforward. But for matrix multiplication, you have to observe a few things first of all. So now, the first thing you have to check is the order of that matrix. Now, let's work with this example right here and imagine we want to multiply them. Now, I told you that you check the dimension first of all, right? So this is what? A 2 by 3 matrix, right? And then the second one is what? Another 2 by 3 matrix, right? Now, the first thing you have to check for in multiplication is these two dimension of these matrices. These two numbers must correspond. If they don't correspond, that means you cannot multiply this. You cannot multiply these two matrices because the 3 here and the 2 here are not matching. Now, if this was a 3 by 2 matrix, you would see that the 3 here matches the 3 here. And now you can go ahead to multiply. And now the sweet thing about matrices is that you can even know your outputs beforehand. Because since this 3 and 3 match, then you know that the output of your matrix, of your product matrix, is going to be what? A 2 by 2 matrix. Yes, exactly. So unlike addition, where you add it when they are exactly the same, and then your answer is exactly the same, it does not work the same multiplication. So you have to first of all check, okay, can I multiply these two matrices? If you can, then you can also predict your answer and then you go ahead, right? So if I were to multiply these two matrices, it will not be possible because, of course, this is 2 by 3 matrix, this is also a 2 by 3 matrix. So in that case, it wouldn't work. However, if it does work, what you do in matrix multiplication is to multiply the row with the column, the row with the column. So you take this row now, and so let me show you why this is important. Checking dimension is important. So let's say we're multiplying these two numbers now. So you take this row and then you multiply it with this column, right? So this is what row 1. There are 3 elements. So you do 3 times 2, right? And then you do minus 4 times 4. And then you now do 2 times. So you see why we cannot multiply this, because this one now has only what? 2 rows. However, it was a 3 by 2 matrix. It will have what? 3 rows, and you will have something to multiply this last term with, right? But because it's only 2 rows, you cannot multiply this, right? So that's how it works. So now you would have what? 3 times 2. Then you now do plus minus 4 times 4. Then you now do plus 2 times whatever that last one is going to be. And then when you now finish, you now come and write that answer you get in the top left, right? So let's say it's 10 you got. You write it in the top left, right? Because you started with row 1. Now you take the next one, row 2, and you do that same thing again, right? So you take row 2. So you do minus 1 times 2 plus 0 times 4 plus 5 times, maybe we imagine it's a third row here, right? And then when you get that thing, whatever you get, you now come and write it in what? Row 2. Let's say you got 19. Fantastic, right? Now, the next thing will be you go back to row 1 again. So you take row 1 and now you come towards the second column. So you do this row times this column. So you do 3 times 6 plus minus 4 times minus 3 plus 2 times whatever would have been here, right? And now you get another answer. What is the answer? You add it up and then you write it. So let's say you get 3. Fantastic. Next, you take this one again. So minus 1 times 6, 0 times minus 3, 5 times whatever the last one will be. You get what? 4. Imagine. Now, the next thing now is to multiply the last column. So you take the first 3 again. So it's always a row times a column. A row times a column. So this is 3 times minus 1 plus minus 4 times 2 plus 2 times whatever the last one will be. So let's say you get 5. Now minus 1 times minus 1, 0 times 2, 5 times 7. Add everything together and let's say you get 14. Now this answer, this matrix that you're seeing here, is the answer to the multiplication of this matrix and this other matrix, assuming this matrix is multiplicable, right? Because we imagined that it was a third row when we did this. And so if you want to check whether your answer is correct, this is a 2 by 3 2 rows and 3.2 by 3 matrix. And then imagine we are multiplying with a what? A 3 rows, 3 by 3 by 3, because this is 3 columns, 3 by 3 matrix. Now, when I said in multiplication, these 2 will match, and then your final answer will be what? Take this one, 2, and then take this one at the end, 3. So your final answer will be a 2 by 3 matrix, which is what we have here: 2 rows and 3 columns. So your multiplication is, the order is correct. Of course, your math or your algebra can have mistakes in it, but basically that is how you multiply matrices. So you take the row and multiply to the column. Then you write that. Take this other row, multiply to the column, you write that. Then you proceed to the next column, take the row, multiply to the column, and like that, like that, like that. However, this is after you have confirmed that you can actually multiply matrices. Because in this particular case, it's not possible, right? Because these two numbers were not going to tally up. However, if you were multiplicable, then this is the process you would have to go through in order to multiply the matrices. So I hope that explanation was clear. I know it's kind of difficult because you're not able to write these things out ideally, but I think my explanation was clear enough. If there are any questions, feel free to ask. This is time for your questions. Feel free to ask, and I will do my best to explain those questions if you have any.
Under inverse function, please drop more explanation.
I heard what you said. You said I should explain more on inverse function. So let me do one more example under that, so that will become more clearer. So let's see. So let's say that we have, first of all, let me clear this one. So let's say that we are given, Chibike, I hope you're on the call and you can hear me, so that I give this example.
Yes, sir. Yes, sir.
Okay, let's say we have f of z. Something very arbitrary. So z 2, right? Then 1, and you're asked to find f inverse. F inverse of z. Okay, that should be -1. So that's inverse -1 of z. Now, remember what I said. So you are given this f of z is z plus 2 over 1. So how you begin is you replace f of z with another letter so that you can, it enables you to be able to solve it effectively. So normally you just replace it with another variable that is not here. So you just say y is equal to z plus 2 over 1, right? And now your aim is to now make z as rate of the formula. So z should stand alone. Now, so this is y equals to z plus 2 over 1. So you cross multiply y times 1. So it's still y equals z plus 2. And then z now will be what? Equal to y minus 2. Now, having gotten here, what do you now do? Your z now becomes f inverse of z. So this is f inverse of z is equal to what? Y now goes away and you place it back to z minus 2. So now this z minus 2 is the inverse function of your original function, which is z plus 2 minus 1. Z plus 2 over 1. And of course, it is in terms of z as well, because the function, the a main function is Z and the inverse function is Z. So all of them must be in terms of Z. So once you are done with that Y that you put in, you take it out and replace it back with Z, and then your Z now becomes F inverse of Z. I don't know, is that clear?
Yes, sir.
Okay, fantastic. Yeah, any more questions? Any more questions? I think this is where we are going to draw the curtains for the night. So yeah, so today we've been able to go through functions, mappings, and matrices. Sadly, we did not begin on time, so hopefully we had a little technical issue at the beginning, so hopefully that will be rectified subsequently. But I think we're able to cover the bulk, not everything of what we set out to do today, and we did it within the required time. So I thank you all for turning up for the class. Thank you all for being engaging. I think this was one of the most engaging classes I had. So it's better when you have questions and clarifications coming when necessary. So thank you all for your time and engaging when necessary. I hope you have the class has been worth your time and value. So I guess draw the curtains at this point. Good night, and then we'll see you all next week. Adios.